Hey again, here we go into a very rad new convergence and divergence test. This one's actually extraordinarily important, but also very simple. It's known as the P-series test. Why do we call it the P-series test? Well, it's because in most textbooks and in most mathematicians' minds, including my own, we use the exponent P to describe the exponent in a series. So essentially, if you have a series of the form 1 over n to the p, evaluated from n equals 1 to infinity, it's known as a p-series, right? So if you stretch this thing out, that would look like something like this. 1 over 1 to the p, which would just be 1, plus 1 over 2 to the p, plus 1 over 3 to the p, plus, and so on and so forth until you get 1 over n to the p. And it just keeps on going and going and going. So when does it converge? Dude, it's super simple. It converges if and only if p is, you ready for this? Greater than 1. That's it. And it diverges if p is less than or equal to 1. Technically, a p-series is only if it's greater than 0. So you're going to see this in a lot of textbooks, but just think of it as less than or equal to 1. And we'll go over why that makes a lot of sense. But first, we're going to go over how to use it and when to use it. So when to use it? Well, anytime a series resembles this form, quite literally. So you could have a series like this. You could have n equals 1 to the infinity of 1 over n to the 3/2. That would be a p-series. Or let's do one like this. And it might not look exactly like it to start, but we could do like 1 over the 5th root of n. And you might be like, that's not a p-series, except you look at this and you think, wait, that's 1 over n to the 1/5. So anytime you have just one variable, n, k, j, whatever your textbook or your teacher uses, that variable is what the index is being plugged into, raised to some power in the denominator. So it converges if p is more than 1, and it diverges if p is less than or equal to 1. That's it. Okay, so where does it come from? And actually, believe it or not, this comes from the integral test. So I'm going to show that at the end of this video, but first we're just going to use it. We're going to see how simple it is. As always, when you justify your answers, you're going to first, in any order actually, you have to state the following 3 things: the test that you use, the conditions of the test, and whether we converge or diverge for that series. So the sum from n equals 1 to infinity, that is the harmonic series. We can expand it out if you want to, or you can just look at it and say, well, that's a p-series, right? It's 1 over n to the 1 right there. So I would say that this series diverges because it's a p-series with p equal to 1, and that's all you have to say. So this series, make that look like an S, this series diverges, and I'm going to write out the formal justification here, because it is a p-series, there we go, with p equal to 1. That's it. You name the test, you name the condition of the test, and you have your conclusions. Very, very quick. How about this one? Well, this is also a p-series, right? It's 1 over n to the p. And in this case, the p-value is 2, which is greater than 1. So I'm going to say this series converges because it's a p-series with p equal to 2, which is more than 1. So this, and let's make it nice. This p-series converges because p is equal to 2, which is greater than 1. That's it. Name the test that we used, we have the condition, and we have our conclusion. How about this one? Well, I'm going to rewrite this one so that it looks a little bit more like a p-series. N equals 1 to infinity of 1 over, this would be n to the 4/3. Ooh, that's more than 1. Therefore, we converge. So this p-series, or this series is a p-series which converges, or however you want to say it, this p-series converges since, I'll change it up, p is equal to 4/3, which is greater than 1. There's the condition, the conclusion, the name of the test. All right, last but certainly not least, this series is not quite looking like a p-series, but it is one. That is 1 over n to the 1/4. So this p-series diverges because your p-value, the exponent down here, is less than 1 or equal to it. So this p-series diverges since p is equal to 1/4, which is less than or equal to 1. That's all. Now, if you really wanted to, I think it's worth your while when you practice these things to expand them out a little bit just to see what it looks like as an expansion in case your teacher instead gives you a series like this and it's a little bit harder to recognize. And you say, okay, this is 1/4 plus 1/9 plus 1/16 plus 1/25. And you might look at that and be like, that's a p series? Well, when you generalize it and you see the nth term is 1 over n squared, then you'll be like, oh yeah, that's a p series. Same thing goes with something like this, right? 1 over 1 to the 1/4 plus, and I guess you probably write it as a fourth root. You could do that, 4th root of 2 plus 1 over the 4th root of 3 plus, and so on and so forth, until you get out to 1 over the 4th root of n. And then you'll recognize that and say, oh yeah, that's a p series. It's the same as n to the 1/4. So just in case your teacher or professor gives you the expanded form first, it might be worth your while to write it in summation notation so you see that it's a p series. That's it. How simple is the p series? If you're in the 1 over n to the p format and p is greater than 1, then we converge. And if it's less than or equal to 1, it diverges. Now the question becomes, but why? Right? Why does it converge when p is more than 1? Why does a p series diverge when p is less than or equal to 1? So, as I put right here, the answer is actually found with the integral test. Isn't that fascinating? So, the integral test, even though I'm meh on it, I've expressed my views that I'm like, the integral test, it's extraordinarily important in that it proves that this works. And the p series becomes a very simple yet powerful test that we're going to use in other tests as well. So, it's a real link for us in this convergence divergence world. So how do I show that this thing converges for greater than 1, diverges for less than or equal to 1? If we expand this out, we're going to see we get 1 plus 1 over n to the p, that'd be 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, plus dot dot dot, until we get to 1 over n to the p. Now notice that this series has terms that are all positive. They are continuous, right? This function is going to be continuous, and all the terms decrease as n goes on and on and on. That satisfies all the conditions in the integral test. So what we're going to see here is when we have the integral from 1 to infinity of 1 over, and I'll just do x to the p, watch what happens when we integrate this. Right, so this is equal to, we know it's the limit as a goes to infinity of, well, I'm going to do this all in one fell swoop. So if we integrate, actually no, I'm not going to mess around with stuff too much. But when we integrate this, we're going to see that there's a tipping point for this value. We actually, if you were paying attention in my chapter 8 video with improper integrals, you'll actually see that I kind of already went over this idea, we just didn't call it a p series. So we integrate that, you add 1 to it, right? This is x to the minus p. So you add 1 to that, that's minus p plus 1 all over minus p plus 1. And that's evaluated from 1 to a. Okay, so now what does this have to do with anything? Well, here's the thing. When we take the limit as a goes to infinity, we're going to get x to the minus p plus 1. Well, that x, remember, is going to a. To the minus p plus 1, which is going to infinity. Okay, again, why does that matter? Well, let's just plug in the 1 here, so that's going to be just 1 over minus p plus 1. This part doesn't matter. This is where the action is. So remember what we said, that if p is greater than 1, we converge. Well, why is that the case here? Let's think about this. If p is greater than 1, let's pick a number like 3. You'd get infinity to a negative exponent, which is 1 over infinity, which goes to 0, causing this to converge. But if we are between 0 and 1, if we're equal to 1, then this thing is infinity to the 0th power, you would think, but actually no. If it was equal to 1 to start with, you'd get 1 over x, which is ln of x, and ln of infinity is infinity. So we diverge at 1, and then let's say we pick like 0.5. Now you've got infinity, that's a, to the negative 0.5 plus 1, that's infinity to a positive power. So the infinity stays in the numerator, and you end up with positive infinity. And that means that we end up diverging. So it's because of the integral test that we're able to say with confidence that p's got to be greater than 1 to converge and less than or equal to 1, but above 0 to diverge. That's it. So it's pretty neat. So we use the integral test to prove that the p-series test works, Bottom line, P-series test is super simple to use. It makes a lot of sense. If this value is more than 1, we converge. If that value is less than or equal to 1, we diverge. I will see you in the exercises. We'll be doing a lot of these. Peace.